Are we ready? Is everybody ready? Say yes.
Hey.
All right, awesome. Okay, so deep learning is hot, we all know that. Now the question is, who's the best in deep learning? That's why it's called the shootout panel. I don't think anyone here will claim that they're the best in deep learning, but there's different strengths, right? H2O's strength, for example, is the ease of use. One line in R and Python, you get a model. The weakness might be that you can't do this image classification, as I mentioned earlier, that you can't do speech, that you can't do text. So it's pretty severe limitations, but anything else it can do. So now, what's the strength of Café? So this is Cyprian Noel, and he's the expert of Café, and you'll probably be able to tell us what Café is good for.
Mm-hmm.
Just to summarize it real quick.
Yeah, Café has been there for a while, a couple of years, so there's a large community. It has received contribution from many sectors of industry, like Nvidia has contributed a lot, Intel, and so they optimized it a lot for their particular platform. And so in many ways it has very high performance. And the scale of the community means they have most models are already available. So you can go to, there is something called the Café Zoo, the model zoo, and you go there, and whatever you want, there will probably be a model already there for you. From academia or from industry, somebody will have done it probably already.
Great, and Fabrizio, you're the expert for TensorFlow?
Yes. The main thing was, I think the data flow graph is a very powerful paradigm, and it allows you to construct and manipulate the execution of your model itself. Besides that, a good point is you have Google behind it. It has a lot of resources and a lot of good people working on the primitives of deep learning. And finally, you have a big community. That's a lot of people are contributing and putting a lot of effort in adding more and more models and good stuff to the repository.
Thanks. And KK, you're the expert for MXNet?
Yeah, you can. For MXNet, we can say we are the most portable platform. We are the most lightweight. You can run MXNet on any hardware if you have a C++ compiler. And we have very few dependency. Actually, the only dependency is you need a BLAS, a basic linear algebra subroutine. And we do not need other libraries. We just need a BLAS.
Great. So Mark, he's our expert data scientist who doesn't use deep learning that much. So we'll get to ask him, why would you consider using deep learning now that you've...
Yeah.
Have you ever had an issue where, like a problem where you were wondering whether deep learning could help you?
Yeah, actually, I mean, I'm curious how we fit more and more problems that way. Like, it feels like I can spot a data set that looks like deep learning would be a good guess, and it has a lot of numerics, it's nicely bound, but I'm sure that's not the real range of it. So what I'm curious, as we explore multiple libraries, how can we figure out how to get more things through? We have really good recipes. I mean, if you're doing image and you're not doing convolutional neural nets, you're kind of doing it wrong. And you can see the comparison of like when Hinton will post his benchmarks and all of the old school ways of doing it, and it's the exact promise of almost machine learning. You have a bunch of business rules, or you just let the machine figure it out. So that we have these recipes essentially for all the things Arno just talked about 5 minutes ago. But I use GBM like a sledgehammer. I want to maybe not do that all the time, and so signal processing would be interesting because it feels a lot like something where maybe we can come up with more recipes, design patterns to get deep learning in there. I don't know one from the next, but I want to explore that.
So people always ask, like, okay, now I get it, deep learning is powerful, but isn't that still a kind of black magic? How do you configure these 150 layers, right? You look at the inception model or ResNet, you have hundreds of layers, and every layer has a certain set of parameters to parameterize it. There's these building blocks. What happens if you change one of those? How bad is that? Or how did they come up with that? How do you build deep learning models, Cyprian? Do you just, kind of that you take as many neurons as you can and you train it as long as you can, and in the end it's going to be good? Or is there some tools that help you figure out which ones are more promising, so you can terminate them early? Because training takes time, right?
Well, there was a long effort to try to formalize that a bit more. It seems like it's still a bit intuitive, and I heard a paper a few weeks ago where they tried very advanced hyperparameter optimization, like Bayesian optimal stuff, and the result seems to be about the same as random search. So basically, there are tools that can help you search around the space of possible models, but there is not really a theory, from what I understand, and people resort to a lot of brute force, trying many things, having very good systems and tools that make you explore the space as fast as you can. And if you play intuitively, you get the sense relatively quickly if a model doesn't seem to converge for something. You don't have to train for like 3 days on a big system. So you just try things, play with different variations of models, and set up a good environment where the system will automatically try, explore the space, help you. But it's mostly about getting good tools that help you explore as fast as you can, and developing an intuition about a particular problem, because that's apparently still as good as it gets to just intuitively try things.
So it looks like the tools to train models are open source, but the tools to explore the models are not as open source, right? Or
there are startups doing hyperparameter search, things like that. It's true that I don't think there are any very good tools. There are things out there, and it's something that can be built for your particular use case, where you have a part of your system will launch jobs on a cluster and try things and then report what it finds. It might be a bit ad hoc still. It might be some things that we could help people deploy and get right. Yeah.
So how do people train TensorFlow models at Google? Do you know? Is there something you can learn?
I haven't worked inside Google, so I don't exactly know how they do it. But I guess they will leverage their entire infrastructure to actually try. More general about deep learning models is very empirical. These things are trial and error. There are some guidelines and some basic steps that you have to know to improve the models, variable initialization, and using the right layers on images. Now you're not going to use straight RNNs on images. Besides that, there are a few tricks, like you want to counterintuitively optimize and overfitting your data at the beginning, just to make sure that your network is working, and then try on a bigger data set and try to generalize out of that. Specific to TensorFlow, there are a lot of very good models out there already available that you can start and don't reinvent the wheel. Also, like there are the inception model is already there, trained on the Google data set, but then freely available, so you can remove the last layers and just optimize for your specific case. So that helps a lot.
As a student, you say you get study. I'm an expert on MXNet. This is one point I do not want to admit, because in most time, personally, I do not have a very good idea about how to choose the network, how to design my own networks, because this is something more like art, not like a science. You see a data set and you see the result. Some people will have the feeling things, okay, we need this kind of layer at some place. But I think this is still in the research field, how to build your neural network for your specific problems. And I have to say I do not have a very good answer.
Yes, there was some recent paper that during training, it actually reconfigures the network, so it learns how to configure the network. But it only works for small network, and it's like prototype research, so it's very early still. But you would think that the architecture of the model itself is also a parameter, if you want, or a set of hyperparameters. So why don't you tune that, right? But of course, it becomes more and more complex. You can try everything; it takes forever. So, how much is it worth to get to a better model in the end? How much time do you want to spend? And how efficient is it? But it seems that it's worth it, right? The deep learning models are getting better in the end than other models, especially for these structured problems where you need to find the structure of the image, the structure of your speech, the structure of the text. So I think the reward is worth it, but we're still struggling. We're still walking barefoot from here to Europe, basically, just to get there, or the other way around.
One key insight is these things you can think, all these different neural networks configuration, you can think as building blocks. So you can really Lego, you can put them together and try to solve different problems just by composing them. So it's not one single algorithm that you use it for one specific application. So you have convolution network, you have a recursive neural network, you have other tricks that you can combine them and solve higher and higher problems. Now there are like a study on how to use external memory to actually come up with a very good way of interacting, the famous chatbots. And there is a lot of neural networks inside that model. So I think is one key part of this technology that I really think is different from before, because before it was only one single algorithm that you have an input and output, but it was very hard to actually compose and create more and more sophisticated algorithms. So I think that's very, see the deep learning networks as building blocks and composable structure that you can Lego block them. And
yes, and those Lego blocks you'll be able to use as customers of H2O, right? You'll be able to, you say, okay, I want to turn my images into usable features for my GBM models. So give me 1,000 columns of numbers for each image that I have. And these columns will be representative of probabilities of things that are in the picture, for example, that you care about. So you can make these either classification probabilities or just inner features of the neural network, whatever that's worth. And the GBM can mine that too. So you'll be able to say, okay, make me image features, or make me text features, or make me speech features. And you can hear if somebody's yelling agent, agent, agent repeatedly, right? And that could be a feature that you can like just extract out of the audio signal.
Well, and that's what intrigues me about as the GPU cards keep arriving in the office. I'm starting to play with these things a lot more. Thinking of building blocks feels like that's the workflow of a mature predictive modeling workflow, I guess. But thinking of solving these problems, like we have a simple one where there's a way to do regression, classification, then regression. If you have a really sparse target, maybe you're just going to figure out zeros and ones first, and then you're going to try regression after that to actually figure out the number. That's a good pattern. So how can we find those kind of patterns in deep learning to wire them at? So that's encouraging to hear that, because that's what it seems would draw me to it. Like you're a token traditionalist on this panel. So how does that work? Like we have these recipes. How can I wire them together and make better things as a big product of everything? So that's intriguing.
And this idea of building blocks is really something that I really like, because then it becomes, I mean, it's cool for me because as a systems guy, because then it becomes a problem of how good is your infrastructure? Like how fast can you try things? How many combinations can you try in a single day? If you spend your whole day doing like nitty-gritty plumbing stuff and wasting time, and so how much are you willing to invest upfront in your infrastructure to have very good, very fast tools, good visualization, so that you can spend your day in a very efficient way, like querying the data you want, and you get a data set, and then you try things, and you launch many experiments at the same time, and you keep your infrastructure busy all the time so that it's constantly leveraged as much as you can, using the most efficient devices for the most efficient tasks, and, like H2O for parsing, GBM, GPUs for actually crunching the matrices and stuff like that. So yeah, there's lots of exciting opportunities in a systems domain, because for machine learning, it really makes a difference. Like before machine learning, you could get away with like infrastructure that was not very efficient. You could just throw more machines at it. It doesn't work anymore. Like now we have to really think through getting the best tools, because it will make your day just crazy more efficient, like several X more efficient.
And something interesting about the workflows too, I just thought of is, I hope this isn't outdated, but a couple of years ago there was the idea that Jeff Hinton had this dark knowledge that and H2O would bring this to the table. The idea is that you train a giant model to get a pretty good opinion of a binary classification model, and you get probabilities out of that, and then you tune a much simpler model on the output of that. So it's like using all the goodness of deep learning that's very complicated, and in the end you end up with something that's a little more scalable to put your predictions out. So I think that's something that we bring to the table, is that industrial use case. To be honest, I don't know how that fits in where we're going, but those kind of patterns intrigue me, where you're really actually trying to deliver these predictions at speed, and that's what the interest was of that workflow again, of kind of a two-stage kind of thing. So.
Another thing that interests me is the ability for these models to come up with features, right? People say, okay, you don't need to do feature engineering anymore, you don't need data scientists anymore, deep learning does it all for you. But I don't think that's true yet. Imagine you have a data set that tells you, let's say every event is like, every column is a day, and then there's 0 1s whether you bought or not, right? Now deep learning could sum that up and say, okay, for every person, how many non-zeros are there per row? Or it could compute for this week of the 7 first days, how many actions were taken, how many ones, and then for the second week, how many ones. And in theory, deep learning could make its own column, if you want, that has these partial sums. But is it really going to do all that on the fly? And is it going to be... The first question is, can it do it? Yes. Second question is, will it do it? Maybe. Third question is, does it hurt to just do it up front by hand and say, I know this is a daily event, yes, no. Why don't I make my own summaries that say for each week, how many times does it happen for the last week, for the last 2 weeks, for the last 3 weeks, how many times? And I just make these extra columns, and then my model can just mine that, and it's going to be much easier for the model to start from there instead of having to figure out all these counts itself. So Mark always makes these features on his own, right? These kind of grouped counts and means and medians and all that. I don't think there's anything better than human brains to make those features right now. I don't think deep learning is there yet. Do we have any evidence to the otherwise, to the contrary?
So there is a new, Google posted something about deep and wide networks. And the idea was you have your features, human coded, and then you encode those features with a neural network. So the neural network will kind of embed the data set in this hyperspace and come out with a new set of features. And then the final set of features will be yours plus the one encoded by the neural network. And then you can pass that through your normal pipeline. And so, yes, I agree with you. Deep learning are not at the point to take a generic data set and create features out of it. But what they are good at, it seems, and this is with the example of word to vectors, where you get a phrase and is able to encode in a numerical way that you can then use. So we'll get there. We'll get there, and it's going to be pretty fast, actually, how this thing will able to reason about the data. And maybe it will be some future that we can implement in our framework. It will be
at least it's a good second opinion, right? If you have a deep learning model that's really smart and figures out all kinds of stuff, and then you have the human that says, I know what I need to look at, maybe together they will be more powerful than one alone. Mm-hmm. Are you scared yet that someone else will win Kaggle with just a deep learning model on every problem? You don't see that, right?
It happens every now and then. I mean, Hinton himself actually won a Kaggle competition with a group from Toronto, almost just to prove the point. Again, it had that feel of a numerical data set, but nonetheless, it was not one for which we have a recipe, certainly at that time. That was about 3 years ago. So And that was their point. We didn't have to think about the features here. You did gather that they had that intuition about the right architecture, and they wouldn't divulge what that was. So it's hard to get that knowledge of what these architectures are, but the world will keep creating more of them as we go along. But another one, even one I did, someone figured out a different way of encoding an RNN structure, and they took something that didn't have to be a time series, so they kind of used a little bit of intuition to structure it in a way that deep learning figured it out. And they wrote a great blog post of all the little building blocks they put in. Let's try bidirectional. Let's try all these little bits and encoding different bits of the network as it went along. So it's a nice tutorial as I'm kind of trying to learn this space through. But I think the trick there that they're not really letting on to is they also encoded what they were trying to learn in a special way that isn't obvious to everyone, but hopefully we can start learning these patterns. So.
Does the audience have questions? We have 15 minutes left, so if we encourage questions from the audience. Yes, Wei? Right. Let me throw this microphone. Oops. Okay.
For a long time, they all claimed that AMD card could be supported later, but it never came about. What's the I guess the framework?
So Nvidia has a library called QDNN.
CUDA, yeah.
That library, at the version 5.0 released a month ago, I think, or a few months ago, it has support for convolutional neural networks, so it's able to do 3D convolutions, and it has support for the main signals like sigmoid and ReLUs. It has support for RNNs, and that was the last addition in the 5.0. So yes, it's growing. It's not able to do everything, but I think the main, most computational expensive primitives are there. And these things are very fast. They're much faster than CPU at the moment.
Well, I think,
yeah,
so Wei, were you asking about the OpenCL?
I was just asking, there's another GPU vendor, AMD.
AMD, yeah.
So a lot of people talk, maybe a couple of years ago, people already say, oh, soon they will support AMD because there is a ACC or whatever, the library.
Your proprietary CUDA on the Nvidia side, and you have OpenCL on the AMD side. Yeah.
The other side also have
nobody picked that up.
API, but
I think there is different efforts. Like there is an OpenCL branch on Café that's trying to run on the other ones, like CPU, AMD, and AMD is apparently trying to catch up because they started this whole initiative to open source all their drivers and implementation. They are probably trying to. That's speculation, I have no idea, but they're probably going to match the QDNN. They are going to do their own implementation of that, because that's the only way they can catch up. And so I don't know. I hear their hardware is actually really good, but you can't really use it because it's lacking the, there's lots and lots of software that Nvidia has been investing in to make it usable. So they are trying. And there is a branch in Café that you can already use. I don't know if it supports. I don't know if it's feature equivalent, particularly for multi-GPU. If you want to scale, OpenCL doesn't have all the primitives for like memory sharing and all that stuff. So you might go some way. It might not be a full match, but for some application it might be better, as good, or maybe better if the hardware is as good as they say. So, yeah.
Eric?
You may have already mentioned this. It's just if you did, just say yes or no. But for those of us who can't afford huge data centers, want to use all the deep learning stuff, if we're spinning everything up on AWS, is there access up there to GPUs or no? Or?
Yes.
Oh, there is?
AWS has GPUs. So you can have a 100-node GPU cluster if you want.
And it's separate from your virtual machine? You configure it separately, or it just comes along with your virtual machine?
It's one of the instance types. So you can just pay a little extra to get a GPU on each box.
Oh, wow. Thank you.
So we'll make images with H2O that are pre-configured to run on these Amazon machines, so that you don't need to worry about the configuration part. Yes, there's a question over there.
Yeah, so touching a little bit on the point you made before, I read a blog post recently that claims that architecture is the new feature engineering. So it sounds like it's basically moving from, engineering specific features to coming with architectures, using, again, intuition to figure out which architectures to use. So just wanted to know what your thoughts on that are.
Yes, very much so. The architecture is the new feature, if you want, and instead of doing a log transform on some column, you'll worry about whether you need a pooling layer or not. I was wondering if there's visualization tools that would give you like real-time insights into the weights that are being trained so that you can get a feel whether it's actually working or not, right? And if you can look at it, then the model can look at it. So you can have another deep learning model looking at your weight distribution in each layer, deciding whether it's good to keep going or whether you should terminate or something. Mm-hmm. So you could add like extra intelligence into the modeling process to figure out what's going on. And make that part of the trainings if you want, right? So we have like hierarchical models that help each other to get better. Maybe there's some hope for that.
No, definitely. Like one paper that just came on in June, it was a neural network within a neural network. Basically, they use a neural network to help the gradient descent algorithm to perform better.
Okay, perfect.
Okay, so exactly. Mm-hmm. And we need tools like that. We will need, there is no good way of taking a layer and run normal statistical analysis on it. And that has to have a very firm properties of statistics. It's not just random. It has very structure within it. So there is no easy way right now to inspect and have like that very fast feedback that you want to build these things.
It's great. Any other questions from the audience, or shall we continue with our little chat? There's one more over there.
Hi. I was wondering, so initially, artificial networks got a lot of cues from biological networks. So there was a sort of positive feedback loop there. I was wondering if there was going to be a sort of another type of mutualism with other type of optimization algorithms, specifically genetic algorithms, since they're responsible actually for giving rise to each one of us. There's been some success out of Cornell along these lines, but I was wondering if H2O had any plans to come up with a distributed GA algorithm.
So the question is whether we'll have other optimization algorithms that mimic let's say, the nature of the brain in terms of learning stuff, or somewhat at least biologically inspired learning algorithms, and not just the current backpropagation or the current brute force grid search, even if it's randomized. Yes, I think it's fair to say we'll do whatever it takes to get to the state of the art, right? And if there's papers that prove that it's valuable, then we'll do that. But we'll probably not be the ones writing those papers. We'll probably be a small step behind, making it enterprise grade, whatever is known to be good.
Yeah, Geoffrey Hinton has given a talk a couple of times saying that backpropagation is actually biologically inspired, which I don't know how valid that is, but he really seems passionate about it. So, and in practice, evolutionary algorithms seem to have been tried for 1 million years, and they've been tried a lot. Like the SGD, it's not like SGD is whatever we have now. Like people have been just going at that problem for decades and decades. Like people in optimization, people in convex optimization, they have formalized it and worked on it for decades. Really, really smart people, and we are still using SGD because it seems to still be the best. SGD is a good second order thing to make the scheduling right. Seems to be still the best out there by far. So
That's how we do, by the way. Our adaptive learning rate is using second-order information to do a per-weight learning rate that's time-dependent. So it's not just a constant learning rate per weight, but it's adaptive. Maybe a quantum computer someday can just solve the whole problem in one step. Right?
Yeah, that would be ideal. No? They will flash immediately the weights to the perfect situation where
yes, it'll just
they minimize the loss time.
Yeah.
They're working on it.
Yes. Yes?
Besides vision, speech, what other problems are does neural network find?
So the question is, other than vision and speech, what else can neural nets do? I guess text, NLP, scene parsing, like video as well, of course. You can look at the sequence of images and come up with what's the next action that's going to happen. If you see two people are going to kiss or hit each other, basically, right? What's the next thing? You can combine those. You can ask what's in this scene here. Like the composition of the scene is that there's a TV, there's tables, there's people, and so on. And on each table there's bottles. You can like zoom in, and maybe there's this attention model concept where you only focus on what matters to you, and you don't look at the whole thing. So there's concepts that are unique to deep learning that might help focus on what matters more, so that we don't have to brute force training with millions of examples just to learn what a bottle is, right? Maybe it can be a little smarter. So I think there's efforts on the way to make deep learning smarter in order to solve problems that are more human-like, like perception of the reality, if you want.
So, like, I had some experience with the images. Like, for a neural network, is it possible you can, besides the image, you can put some other inputs into the neural network?
Yes, definitely. Like our airline example, right, was just regular features. So you can have text going in, tweets, your images in the tweets. You can have audio signal. You can compose all these. And your model can not just predict one thing, but it can predict 12 things, right? You can have multiple outputs. One could be a regression output. One could be a softmax for classification. Then you can go down some more layers. And there could be another classification output. And then you can have a recurrent piece that says, like, if I predict this in the past, then this is what I'm going to predict for the future, or whatever. Like, you can have all these interactions. So I think it's an unlimited complexity that is open for the taking, open to be taken, I guess.
And a simple addition would be like sequences, but time series was up on Arno's notes earlier. So they're good at especially irregular ones. They've been a building block of forecasting for a little while anyway, something to try. But as they get better and better, they'll be better at encoding nonlinear sort of seasonality, things like that.
The way I think you can look at these neural networks, these are general function approximators. So if you have enough data that somewhat describe what's your problem, and the neural network can approximate this function. I have seen applied to energy models. I have seen applied to reinforcement learning, where it only computes part of the problem to try to give a better indicator of the model. So yes, the trick part is the data. You need to have a lot of data, hundreds of thousands of examples to millions to get to superhuman level. And the second part is encode this data in a way that the neural network can apply backpropagation to it. That your model has somewhat be differentiable.
And in some domain where you don't have data, you can use one modality of data to remove it from the input and make the network predict it. So in self-driving, for example, there is work where they will, instead of driving around labeling everything, that's a pole, that's a light, because it's extremely costly, obviously, you can have different cameras, like a depth camera and a color camera and a black and white camera or something. And then you get the network to predict one of the other depending on the other. So it will predict the distance depending on the color. It It will predict the color depending on black and white. And so it's a challenge you give to the network and the signal you give to the network that you can produce as much as you want of. So you can still use supervised training, but you set up things in a way that you can provide as much supervised training as you want without having to manually create the labels. And that kind of trick, if you can figure out that kind of trick for your own domain, then that's it. You have infinite data in your own domain, and the model will, you just brute force it until the model will understand fully what you want to do. So it's setting up the experiment in a certain way if you don't have the data.
There's also this concept of data augmentation. Let's say I only have 2 pictures of this bottle, right? You can rotate it, and you can scale it, and you can distort it a little bit, and shrink it up and down, left and right. And then it looks like 6 different bottles or 15 different bottles. So in the end, you have more data. So that's the cheap poor man's version of making more data, is just to distort it a little bit. That works for image problems, right?
Yeah. Also audio. Actually, that was the trick that allowed Baidu to have a very, very good voice recognition.
For audio.
They scrambled just enough noise in the data to not corrupt the main signal, but to make the neural network more robust and resilient to normal life. No? Yeah, out of the laboratory is a mess. Inside you have all the data nice and curated. So they actually allowed that technique to get 6 times the data set and improve a lot.
All right, we have one more question here.
So I guess it's specific to my problem. The problems that you've described, speech, video, image, it's kind of like pretty dense and numeric data. And then my application is very sparse categorical data. Would it make sense to try deep learning for that type of data where you have mostly zeros, just like a few features, and it's like completely categorical?
I think from my experience, I would say factorization machines or follow the regularized leader. I don't know what other people think. I don't think deep learning is the best because you have all these weights connecting every single possible categorical level to the neurons, and they start out random, so it's a dense matrix that you have to optimize, and it might turn sparse later, but it still will start dense. It's expensive.
Would it help to do like any kind of like centering or some sort of preprocessing?
The weights are non-zero, right? Every single weight is non-zero, so every connection is there. So just to update those connections is expensive. So there's no way to make that network sparse initially. Right. It might always stay non-sparse, so that's just expensive.
One thing you can try is to encode it. Like you take this sparse matrix and somewhat try to find a dense representation of the sparse matrix, and you can adapt.
What kind of encoding are you referring to?
That's something that you have to figure out. Just the idea of having this sparse matrix, and you have some kind of metric that allows you to compress it and create a new dense representation of your sparse one. And then once you have the compressed representation, then you can apply other neural networks to it. So these two neural networks, one to compress, and then you create another one to do the analysis on it. This is just ideas. Okay.
Assuming a lower rank representation is still good enough, right? If they're all individual, unique people that do certain things and everybody matters the same, then there's no way to compress it in a way. But if there's like 50 groups of websites that people click on and the remaining 6 million are all very rare websites, then you could say you get a good model looking at only the top 50, right? Roughly speaking. So it depends on the domain whether the reduction will help, but SVD-based, some eigenspectrum-based reduction might be useful.
User or word embeddings, for example, might work well. So
random projections.
Sorry?
Are you talking about random projections?
Word embeddings.
Oh, let's get the mic there.
Yeah, so for example, in language models, words are typically very sparse in sentences. So you'd have a huge vocabulary with, say, 100,000 words, but in a typical sentence, only about 10 or 20 of them would occur. But you can compute word embeddings that reduces the size of this 100,000 dimensional vocabulary to, say, word vectors of size 1,000. And at that point, you have a much denser input that goes into your into the rest of your neural network once you've computed that embedding. So that's one thing. And if you're talking about users, for example, then you can compute user embeddings based on which users have similar behaviors, for
Cohorts.
example.
I see. Okay.
So there are things you can do.
So with domain knowledge, you can do some mappings and some groupings and so on. Yes.
Yeah, I guess. Word2Vec is somewhat domain knowledge driven, but not too much.
All right, I think the time is up, but we have one more by way. Is that true?
I recently actually heard a talk by Amazon. They also use deep learning for very wide, column-wide problems, classify kind of products or use images, use descriptions, use languages. So they actually have a framework that all your framework is parallel split jobs horizontally. Like
Destiny or so. It's Amazon's, yes. So they have something that optimizes for the sparse case.
Yeah, they split the job
by columns.
Chunks, yeah, by columns.
So they have a model parallelism where the model itself is cut up.
Yes, they claim it's 100,000.
Yes, any optimization for that case will make a huge difference.
Because it's language, because through description, so you can, just like your case, it's
almost
sparse.
orthogonal.
Yes, it's sparse, it's just 0.
It only runs on GPU though.
It runs on GPU, exactly.
Well, there's lots of research needed still and lots of work needed to get it to the average user, right? Most industries are not quite ready to use deep learning today, but they are very interested. That's at least our sentiment. So thanks a lot for participating in this discussion, and hope to hear more from you in the future. Thank you.